All right, welcome to the Chapter 9 quiz walkthrough, answer guide, whatever you want to call it. We've got some learning objectives up at the top, so make sure you look through those. Those are the guidelines that I use for writing the exams. So the questions that I write are going to be questions where I'm asking you to answer questions that meet these learning objectives. So for question 1, it says sort the following in order of increasing energy, and of course I can't see what those options are here. So we have a few different options here. We have, let's see, I gotta write these somewhere. Visible radiation. We have X-ray radiation. We have UV radiation, we have radio radiation, and we have IR or infrared. So for each of these boxes, you have all of these options. We want to sort these from lowest energy to highest energy. Now there are some of these that you might be able to sort of use some critical thinking skills and think about what you know in everyday life, things that you've encountered there. For example, X-rays. You go to an X-ray, there's a reason they put, if you're getting like dental X-rays, they'll put a big metal apron on you. X-rays are going to be the highest energy here. They're the most energy radiation, and so you use lead-lined aprons and things to shield from those X-rays. So you put an X-ray. We'll start with the highest energy, so we'll cross that one out. Now we're left with visible, UV, radio, and infrared. You could always go and look these up in your book. Radio waves have the longest wavelength. So I think they range anywhere from like a meter, maybe longer. Could be wrong on that. So radio waves, or radio radiation, is going to be our lowest energy. Moving up from radio waves, we have infrared. So we have IR. These are mostly just things, you kind of have to know what these are and just be able to go and look them up in the book or look them up on a table. The next is going to be visible radiation, so visible light. Maybe that's one of the things that you can use, is you can move, use that as your baseline. It's kind of in the center, actually, of the energy frequency spectrum, at least the way it's usually displayed. And then higher energy than that, because it's UV light that we use sunscreen to block. So UV light is higher energy than visible light, and that's what causes sunburns. So radio waves are our lowest energy. You never even know they're there, even though they're all around us all the time. Infrared radiation, that's what you use in it's actually what your TV remote uses to turn the TV on and off most of the time. There are some smarter TV remotes now that you can get that don't use that, but it's below the frequencies where we can see. Visible light covers everything from red, so red light in the visible spectrum is the lowest energy. So we have red light, and then orange, yellow, right, Roy G. Biv, green, Roy, R-O-Y-G, blue, indigo, like that, and then violet. Maybe this is more of a violet. So that Roy G. Biv spectrum goes from lowest energy to highest energy. There's actually a great YouTube video, or a music video actually, by They Might Be Giants. Called Roy G. Biv. They have a whole series of fun videos about science. It's nothing super technical, but if you memorize the song, it'll help you memorize at least the visible part of the spectrum, and then if you can remember that red is low energy, then that's going from there, then it's infrared is lower energy than that. And on the violet side of the spectrum, above that we have ultraviolet, so more violet or more energy violet, and then X-rays above that. And of course there are more steps in here between radio waves and infrared, I believe, or microwaves. And then above X-rays we have gamma rays. Okay, so for question 2, we want to sort the following in order of increasing wavelength. So we have all of the same options here, but what I wanted you to see was the relationship between, or what I wanted to test was the relationship between wavelength and energy. So energy is inversely proportional to wavelength. So if you want to write that out as an equation, energy inversely proportional to wavelength, which is V, or nu. So as energy goes up, as we increase the energy of our electromagnetic radiation, actually I think it's like this, the wavelength goes down. It's V is all you really need to know. So our wavelength goes down. So short wavelengths have high energy. So if we go back to our question 1, our shortest or our highest energy was X-rays. So that is also going to be our shortest wavelength. So X-ray. Actually, we'll try to remember to cross these out now. So really, if you know this principle, if you figured out number 1, you can use number 1 to solve number 2. So UV has the next shortest wavelength, because it's also the next highest energy. Our visible light will fall after UV, and then we'll go UV, visible, and then we're just left with infrared and radio. All right, so infrared, radio. So really you just need to know the qualitative or the relative differences between these different types of electromagnetic radiation, and then how wavelength and energy sort of are inversely proportional. Frequency is also in there as well. So frequency, as wavelength increases, frequency decreases. So if we've got our three things here, or energy, and then I'll just write out wavelength and frequency. So if energy is increasing, or if we have high energy, then we have a high frequency and we have a low wavelength. And that's because if we were to plot out one axis of our electromagnetic radiation, if we have something with a frequency like this, or we have some wave that goes like this, very excellently drawn there, the wavelength is the distance between one peak and the next peak. The frequency is how fast these peaks pass a certain point. So if we have another electromagnetic radiation wave, and it looks like this, then our wavelengths are, I'm just going to do it, well, I'll do it right here, right? So our wavelengths, that is the wrong one, wavelengths are shorter, so that means it's going to pass the same point more often or more frequently, and it therefore has higher energy. So this is a good one to remember right here, this relationship between energy, wavelength, and frequency. Energy and wavelength are proportional, so as one increases, the other increases. Increase energy, increase frequency, decrease energy, decrease frequency. And then wavelength is inversely proportional, so it'll do the opposite of what energy and frequency do. If energy and frequency go up, then wavelength will go down. If energy and frequency go down, then wavelength will go up. All right, so question 3. What is electromagnetic radiation? And our options here are a form of energy, a type of reaction, a class of molecule, magic, maybe, or none of the above. Some people would argue that science is just magic explained, and of the things that I know about at least, electromagnetic radiation does act a lot like magic because they don't understand it. But the correct answer here is that energy, or electromagnetic radiation, is a form of energy. Oh, perfect. So we kind of already covered question 4. If you increase frequency, wavelength what, and energy what? So our options here are either increase or decrease. And we're going to have the same options for both of these. So we're just looking at this, but if we increase frequency, then our wavelength will decrease. And then if we increase frequency, wavelength decreases and energy increases. Man, I wrote that so poorly it's hard to read. So it'll increase as well. So question 5. Which of the following best describes the energy of electrons in an atom? So none of these. Or the energy is continuous, the energy is fixed, or the energy is quantized. A little keyword test here. So quantized means that it falls into certain levels, which is why in the book, and I'm trying to remember, I believe in the slides I also mentioned this, that energy is like walking up and down a ladder or walking up and down stairs, but these steps and these ladder rungs on the ladder are at different heights. So you can only stand on, if this is our ladder, you can only stand on each of the individual rungs on the ladder. You can't stand on a place in between. Except in an atom, if our energy rungs look more like this, so you can either stand here, expertly drawn feet, or you can stand on a higher one, or you can go to a lower one. So that is what quantized means. So the energy of electrons in an atom is quantized. It can only exist in certain levels. And that's what was observed, and what Niels Bohr's original model explained was that the electron, or the light spectrum observed when exciting hydrogen, was caused by these individual discrete levels of energy that was able to be occupied by the hydrogen's single electron. Okay, so related question here now. Question 6, light is emitted by excited hydrogen atoms as, or the light emitted by excited hydrogen atoms is specific to narrow frequency bands, unpredictable, uniformly distributed across all frequency bands, or unknowable. Again, Niels Bohr's model was based on this discovery in hydrogen and led him to discover that it's specific to narrow frequency bands. And this is actually true for all elements. They're not as predictable as hydrogens because hydrogen is such a simple system. But if you were to take helium and throw it in there, or neon, and I believe they show this in the book as well, you get very, very specific frequencies of light that are emitted. Question 7. Yeah, so I wanted to make you write here a little bit. Because I think, especially for these quiz questions, the stakes are relatively low, and you can go and look it up in the book. I don't think there was even a time limit on this quiz. But how was the Bohr model of the atom wrong? how did the quantum mechanical model address that issue slash issues? And then make sure you answer both questions. So really what I was looking for here is that you would explain that sort of that the Bohr model did have these quantized energy states. So sort of some of the key ideas that I was looking for. I'm grading these pretty laxly. I just want to see where you guys are at. So quantized energy, that was correct. That was a correct thing about Bohr's model. The incorrect thing was orbits. So these specific paths that electrons take around the outside of an atom. So those were incorrect. So I guess you didn't really need to say anything about quantized energy, but you could say that he explained quantized energy by using orbits, but discovered that he couldn't use his model. So one of the other things that was wrong is that I always misspell Bohr. Bohr's model could not his model couldn't explain more complicated atoms because his model basically said that the electrons aren't interacting with each other. They're only spinning around, getting excited, and then relaxing, and they each have their own orbitals. So the quantum mechanical model addressed those issues by coming up with these ideas of, I'll change colors here too. Orbitals. So instead of having these discrete paths that are taken, the quantum mechanical model says that the electron exists somewhere in this space, right? So the book uses this example of a pitcher throwing a baseball. And that pitcher, even if he's trying to throw the exact same pitch every single time, it's going to land in a certain zone, hopefully in the strike zone. But not necessarily in the same spot every single time, which is what Bohr's model predicted. So the real keys here were that Bohr's model could not explain more complicated atoms because the idea of orbits, and that was corrected in the quantum mechanical model by orbitals. And then also, I think the book talks briefly about waveform functions. You don't need to know what those are exactly, but that those are able to explain how the electrons interact. So, electron interactions. Question 8. So this one should have been a pretty short answer. What are valence electrons? Valence electrons are the outermost electrons. So those are the electrons that are not in the inner shells. So again, if we're talking about our atom here, we've got this, and then we've got sort of a electron probability diagram. Each of these dots aren't electrons, but where they could be. And then we've got electrons that can exist on the outside of that, these higher energy orbitals, and then electrons that can exist in even higher energy orbitals. So it's maybe a little bit hard to see, but these electrons on the outermost shell are at the edge of the atom. So if this atom goes and bumps into something else, it's going to be interacting with those outermost electrons only. Those electrons on the inside are not going to interact. Just like if you crash your car into something, it's the outside of your car that's going to interact, and not the inside of your car. That's a terrible example. But the outermost electrons are the valence electrons. All right, so question 9. How many orbital subshells are there in the n equals 3 principal subshell? Mostly I wanted you to go and find, what is this, figure 9.19 in your textbook. This is the title of that is whoops, I can spell, subshells. So n equals 3 subshell is 3 principal subshells. Or sorry, 3 subshells and the n equals 3 principal subshells. Just kind of a go look up where it is. Up to n equals 4 is as far as we're going to go, and that's 4 subshells. So for each of those principal subshells from n equals 1 to n equals 4, the shell is the same number of subshells. Question 10. What shape best describes the 2p orbitals? And again, you can just go find this in the textbook. Figure 9.21 has the 2p orbitals. And the 2p orbitals have sort of these dumbbell shapes. So kind of hard to see what's going on here, I know. But they're on these 3 principal axes. So the black and the red are in the same plane. And then so this is Y, red is X, and black is Z. So they exist on this plane. So a single 2p orbital looks most like a dumbbell. The sphere would be the S subshells, and across is what the D subshells look like. Question 11, what is Hunds rule? Hunds rule is just something that you got to memorize, but this is where the idea of the hotel is pretty handy, so that if the electrons in an atom are checking into a hotel, they prefer not to share beds first. So if you draw out your orbitals, let's say for the 2p, then if we had 2p3, then we'd have 1, 2, 3 electrons. So those electrons would spread out as much as possible before pairing up. So electrons fill all available orbitals before pairing. Question 12. What is the complete electron configuration for phosphorus? So this is where periodic table, again, you're going to want to have that on hand. I've got one just over here. So phosphorus, just identify where that is on the periodic table first. And I wanted you to write out the entire thing here. Because I'm handwriting it, I'm going to write the numbers as subscripts when they need to be subscripts. So we're going to say, we start out with 1s2. So that covers hydrogen and helium. And then we'll do 2s2, which is lithium, beryllium. Then we'll do 2p6. So that's boron, carbon, nitrogen, oxygen, fluorine, and neon. And then we'll go 3s2. Now we're to sodium, magnesium. And then we do aluminum, silicon, and then phosphorus. So then we'll do 3p3. Now if I allowed it, you could use a noble gas to abbreviate here. And you would start with neon, since that is the noble gas or the next noble gas in the line above, or the noble gas from the line above, I guess is the easiest way to say it. And so we'd start with neon, and then we would start this at 3s2, 3p3. And that represents the electron configuration, so it identifies all of the core electrons as well as the valence electrons. And especially when you're writing it in this noble gas notation, it's got all the core electrons that neon has, and then you're only writing out those valence electrons. So the correct answer here, again, was this one. But on an exam, I might have you do both, or one or the other. Question 13. How many core electrons does elemental magnesium have? Just wanted to note here too that elemental magnesium does not have a charge, which would change your answer, because electron configurations are based on the number of electrons. So there's two ways that you can do this. You could, as I just noted in the question before, write out an electron configuration for neon, or just look at neon's electron configuration, because those are going to be the core electrons for magnesium. Since neon is the noble gas in the line or period, right, row 2 above magnesium. I'll write out the electron configuration here. So we have 1s2, 2s2, 2p6. So the number of electrons in each of these orbitals is denoted in this superscript. So we can add all of those superscripts together. So 2 plus 2 is 4. And then 4 plus 6 is 10. So magnesium has 10 core electrons. And it also has 2 valence electrons. Question 14. How many valence electrons does elemental bromine have? This one is a bit of a trick question. So we can write out the electron configuration. So bromine is in period 4, or row 4 on the periodic table. And then argon is the noble gas in the line above that. So we can start with the argon here, since we're only concerned about the valence electrons. So if we write out this electron configuration, we're going to get 4s2, we're going to get 3d10, and we're also going to get 4p5. Now, 3d10 is 3. 3 is a lower energy level than 4. As that principal number increases, so does the energy. So these are actually inner shell electrons, but this is the electron configuration. So we're only concerned with the electrons that are in the 4th principal quantum shell. So we're going to get 2 plus 5, which is 7. So we have 7 valence electrons. So I hope that was helpful. Practice those electron configurations. They're very useful. They contain a lot of information. They're not too hard to write out. Okay. Yeah, hope that was helpful.